or to Lorne, you mean?
Yeah. Thanks very much, colleagues. This is Mike Anthony, and this is the April 18th meeting of the Education and Healthcare Facility Electrotechnology Committee. We have on the call colleagues from the University of Alberta and from Michigan State University and the University of Michigan. We have Raymond Moll, Lauren Clark from Alberta, Kane Howard from Michigan State, and Jim Hartford from the University of Michigan, and myself. So just very briefly, we meet every other week in Europe and America, and we try to put an agenda together. This is our European agenda. This is the U.S. agenda. And if you're welcome to come to the site and look over what we're able to do in your absence. But in general, we do as best we can to try to keep our colleagues that are running campus power systems apprised of what we're doing. We like to think of ourselves as the place where they all can go for I guess standard of care guidelines, whatever the prevailing wisdom might be. You might notice that from time to time I'm recording power outages. There are power outages in campus power systems on a near daily basis. I don't try to make too big a deal over them, but if ever you need some kind of information about how your system is comparing to others, you have it. So with that, I will turn this over to Lorne, who I hope will say a little something about what he does, and we can get going. It's your airplane, Lauren. You want to say a little about what you do there, and then go ahead.
Sure. So my name is Lorne Clark. I'm the electrical engineer for electrical utilities with the University of Alberta. I've been with the University of Alberta about 11 years, and I do whatever they tell me to do that day. So I graduated from the U of A in 1999, and I went into consulting for a few years. And when I graduated from the University of Alberta, I said, "Oh wow, that's enough education. That's enough higher learning." And I thought I would never come back to the university, but lo and behold, they offered me a job in 2005, and I've been here ever since. It's been a tremendous period of growth for the first about kind of slowed down a little bit for the last couple of years, and it's starting to take back off again. So here we go for another round. So anyway, today I wanted to tell you a little bit about the district energy system that we have at the University of Alberta, just a bit of an overview around that. Then we're going to zoom right into the campus distribution system, or medium voltage distribution system. We're going to look at some single lines, and I'm going to show you some photos and kind of go back and forth between those two different formats after a very brief PowerPoint at the beginning, and then hopefully a little bit of time for questions at the end, and hopefully I don't run out of Mike's 8 hours worth of recording. I expect it'll take about an hour, maybe a little less. So off we go. So, University of Alberta is located in Edmonton, Alberta, Canada. A little bit of history. The original power plant was in service from 1913 to 1963. It was decommissioned after that. The heating plant that's now in place was originally started in 1959, built in multiple phases. 67, 1973, and then 1988 were the large build phases. The original cooling plant for the University of Alberta was built in phases again in 1968 and then expanded in 1983. We also have a thermal energy storage tank, which was built in 2007, and that's just a very large tank that's used to house chilled water as an energy offset mechanism for our deregulated power market. We also built...
Lauren, are you open for questions during the presentation or no?
We certainly could. It might be better to hold them to the end, just for time.
Okay. Oh, thank you. I'll wait.
Which we called cooling plants on campus, which was we built that in around 2010. Another thing of note is we've got about 10 kilometers or 6 miles for people in the U.S. of services corridor, and I'll get a picture of that a little bit later, that connects all the different buildings together for utility services. So the University of Alberta has 5 campuses and multiple land holdings. Today we're mostly going to be talking about our North Campus, or our main campus. Impact on Alberta's economy, about $12.3 billion. We're the 4th largest employer in Alberta. And our facilities are equivalent to the 8th largest city in Alberta. For North Campus, we've got over 100 buildings on 123 hectares of land. We've got over 2 million square meters of conditioned building space. We've got about 15,000 public users that we service every day. I'll talk about that a little bit more later.
Excuse me, let's see, Lauren, I'm not sure, somebody may need to put themselves on mute, so I just thought I'd ask the attendees to put themselves on mute if they're not. Thank you. Go ahead, Lauren.
So in terms of a campus district energy system, we're the largest in Canada, and we're the third largest in North America. For the utilities group itself, we are a public utility. We have a district energy system, as I've mentioned. We produce on-site steam, chilled water, and power. We produce steam from burning natural gas. We distribute through the services corridor, gas, water, sewer, and other utility services as flow through. The sewer is not in the corridor itself. It's below. It's deeper than that. Our customer base. So not only do we service the university itself, we also service the local hospital, blood bank, a cross cancer institution center, and the Jubilee Auditorium, which is a show entertainment pavilion. We service North Campus as well as other campuses as a group for utilities, although we only have district energy on the main campus or the North Campus. And utilities itself has about 60 employees. Specifically for electrical utilities, we were recognized just a few years ago as a utility in the province of Alberta, and the province of Alberta is a deregulated power market, which is a little bit, I think, unique for different jurisdictions. We distribute at 13.8 kV as our nominal distribution voltage. We do have 2 cogeneration units. They're both steam turbine generators that are ultimately fired by natural gas-fired boilers. One's about 15 MVA, the other one's about 31 MVA. And we do participate in the deregulated market here in Alberta in terms of bidding in those assets. We do have a load shedding scheme of cooling plants only, which is on a volts per hertz ratio. We've never had to use it in the time that I've been here. We've got 8 electricians and 2 technical staff, myself and my manager, David Rowe. Why district energy? Really, bottom line, is just a lot more efficient. If you take a typical system, and I think we all know this, if you take a typical system of a remote power plant, which has got all those transmission losses, and you take your typical boiler in a building, which has got a certain efficiency, you add those together, compare it to a combined heat and power system, which is district energy, and you see the ratio there, 49% compared to 75%. A little bit of loading for the greater campus area. So this is, again, North Campus or main campus. So our minimum power demand, about 22 MVA. Our maximum a couple years back in summer was 76 MVA. You see the values there for steam, chilled water, water and gas. Again, that just gives you an idea of capacities. So what's our DNA as utilities for the University of Alberta? We build for the long term. We build in flexibility. We continually invest in upgrading our plant and utility infrastructure. We embrace change that's always happening, always coming, and we provide solutions. At least we try to, as opposed to making problems. So I'm just going to flip over to some single lines. So this is a single line that shows how we interact on North Campus. And everything else I'm going to talk about is just North Campus now, or our main campus. This single line depicts how we interact with the local utility. So the local utility here is EBCOR Power. They have one substation called Garneau Substation, which is at the top here. So basically, this is the magic line in the sand, and this is all EBCOR assets. So they've got a 3-bus system, 72 kV, and their secondary transformer is 14.4. By the time it gets to us, it's about 14.2, and by the time we get it to our customer base, it's about 13.8. So we call it nominally 13.8. But just in terms of architecture, they have the 3-bus system. We get 2 supplies off of each of these 3 buses. So these 2 breakers, one feeds to our cell switching station, bus 1, which is located on the south part of campus. The other one feeds our bus 1 of our north switching station, which is on the north part of our main campus. And then similarly on bus 2, we got 2 breakers, but they go to buses 2 and 3 at the north. And then bus 3 has 2 breakers going to bus 2 and 3 at the cell switching station. And you can see here our 2 steam turbine generators. We do have basically isolation transformers, almost a 1-to-1 ratio, 14.4 to 13.8. And we do that for fault limitation as well as grounding. And they've proven very valuable. something that's kind of interesting to note, we got 2 breakers shown here, and that is accurate. The north switching station, again, is the north part of campus. The south switching station is pretty much attached to the heating plant. These 2 steam turbine generators are in the heating plant, so we ran almost 2 kilometers of cable to get from this breaker that's in the heating plant to this breaker, which is in the north switching station, just because this was the best point to put it in terms of the campus power system itself. So I'll flip from here to our main campus single line, and it's big and overwhelming to a degree. You get used to it after a while, but I just want to highlight a few things. So I zoom over into this area. This is, again, one of those incoming supplies from EBCOR. This happens to be our bus 3 on our south switching station. And as you can imagine, we got main breakers and feeder breakers, just like everything else. One thing that's kind of interesting about the architecture of our specific system is, so we take this feeder breaker, for instance, SF14, which is off of bus 3, and then that goes over to this grouping of switches called a sectionalizing station. And they're basically just dumb switches, big load break switches. You can see we've got we call that a white supply. We also got a blue supply. So we have 2 different supplies. This blue supply here, if you follow it way up, comes off of bus 1 associated with the south switching station. And if you remember, bus 1 was a totally different transformer, totally different supply all the way up at the EBCOR Garneau substation level. So we truly do have 2 supplies coming into this grouping of sectionalizers. Something you'll see a little later from the pictures, these 3 switches that are the blue supply are actually it's actually a different physical lineup of equipment than the white supply. Same room, but 2 different pieces of equipment. So they are separated. From these sectionalizing stations, they do go down into the building, and we'll talk about that a little more in a couple minutes. But in terms of the flow through from the south switching station over to the north switching station, again, you got this blue-white through a set of switches, through another set of switches, finally ends up its way over at the north switching station. We do not operate generally with all of these switches and breakers closed. Typically, we'll say have this breaker open. So our architecture, we call it a complex radial. So it is a radial supply ultimately, but as you can imagine, it's got lots of different configuration options, which gives us a lot of flexibility in operating the system. I'm just going to jump over now to some photos to bring some reality to what we're seeing on paper. So this is a picture of the south switching station. It's just a lineup of 15 kV class switchgear, and you'll notice there's nothing on the doors. We took a page out of the playbook for other utilities, and we took all the protection and control items and put it in totally separate cabinets. So this is a picture of our protection and control cabinets. As you can see, pistol grips and lockouts and amp readings, all those kinds of things. You open the doors, you see all the different protective relays and FT switches and whatnot. So again, we just like to keep that remote from the switchgear. It's one of the things that we can do around arc flash. Again, you don't have to have people there that are interacting with relays, that are doing testing for the relays, or the communications associated with those relays. So just another photo of the protection and control cabinet for the south switching station. So as you can imagine, like every other campus system, we got tons and tons and tons of cable. So we've standardized on a cable type called TEC, which is very similar to MC cable in the U.S. So it's an armored cable that's originally created for the mining industry, and it is applicable to direct bury if desired. Just another photo of a bunch more cables. So this is a picture of our services corridor. So it's a big honking rectangular concrete bunker under the ground of the campus, and it connects all these different buildings together. I mean, you can see the vast majority of it's taken up by piping infrastructure for chilled water, for steam supply and condensate return, all those kinds of things. And you can see the cables, the medium voltage cables, just up here. It's not because it has HVAC units, it's not a confined space because there are air changes. So it's basically like a building underground. Moving on. This is a picture of one of our sectionalizers. We've got several different types of sectionalizers. This happens to be a solid dielectric vacuum load break style with elbows that we can pull off. We've typically used this style for outdoor. It is outdoor rated. In this specific instance, we're using it in a piece of corridor just because of our limitation around size. It's quite a compact design. So you can see here on the end, this happens to be sectionalizer 18. This happens to be the white. You know, we try to do a good job of labeling so there isn't any confusion in the field when we're doing switching and moving loads around. There's a picture of the other half of it, so sectionalizer 18, the blue side. And again, you can see that they're two physical different lineups, blue versus white. You know, again, close proximity, but two different physical lineups. This is a different picture of a different type of sectionalizer. So this is again using vacuum switches. This is just the blue side. I don't have a picture of this white side, but so you have your main incomer, your main outgoer, and then your feeders out to the different buildings. This is a picture of one of our outdoor transformers. This happens to be for a supply to our heating plant. The secondary of this is 4160, and if we have time, we'll get to a single line of the heating plant itself where the steam is created for the campus. This is a photo of one of the larger outdoor transformers that we have. This is the transformer specifically associated with steam turbine generator number 1, is again that kind of 1-to-1 almost ratio of transformer. Like every utility, we got lots of meters, so this is just a picture of one of our meters. Sometimes we get into resident applications, and they wanted a bunch of meters to meter individual apartments, so we did that. And those are those photos. So I'm going to flip back to the main single line. So I just want to dive down a little further now into our system, into a building. So we're going to focus actually on this sectionalizer here, and then the supply out of this sectionalizer goes down into one of our buildings, which happens to be the Edmonton Clinic Health Academy, one of the newer buildings on campus. We've changed the way a little bit that we do distribution. In the past, these would all be fused disconnects. So we're moving to a fixed mounted 15 kV breaker within a protective relay. And that just gives us an opportunity to do differential protection across the transformer and just have better overall protection, lower arc flash, those types of things. Some photos for that. So this is again a sectionalizer associated with that building. Happens to be sectionalizer 22. There's the blue, there's the white. Just a couple more photos of that from the front. So this is the 15 kV switchgear with those fixed mounted breakers here inside of that building. And again, the style of equipment is very similar. We've decided, and we've always had, as far as I know, primary metering. So we meter at the 15 kV level at 13.8 nominally, and we bill based on that primary metering. So that requires some larger metering sections, which you're seeing here in that new equipment. Something just to point out, this is a protection and control cabinet, so the protective relays associated with these breakers inside of this cabinet here. And it's got a little touchscreen HMI as well for electrical control from here of these breakers. You don't have to operate them from the front. It's the other half of that switchgear lineup, 15 kV. So you get to a different room, and you have a separate 15 kV load break just for isolation of this transformer. This is a cast coil dry type transformer, and we've close coupled from this switch into the transformer busing, out of the transformer busing, close coupled to the 600 volt switchgear lineup. I know in the States typical is 480. In Canada, we're typically 600 volt for our low voltage switchgear class. We also have 208 /120, which I know is common through the States and Canada. So that's just one of our switchgear lineups. You can see we've got a main time main configuration here on the secondary, as well as the main time main that we saw on the primary, again, just giving us lots of options for that complex radial supply. And we do have an automatic transfer system for this main tie main arrangement. In case one side is lost, this main would open, the tie would close, your backup. The other side, again, close coupled. This is an example of one of the touch screens that we put in that building specifically. And again, you can operate these medium voltage breakers directly from this touchscreen, just electrically operated through an HMI touchscreen via a PLC control. That control is actually also brought back to our distributed control system. Our flavor here is Delta V for distributed control system, which is typically made for industrial plants. So the distributed control is used for the heating plant, for the cooling plant, and electrical is basically tagged on with that for remote control of breakers in the buildings themselves. This is a different screen just showing the low voltage side. So this is a low voltage switch gear, a transformer, the main breaker. As you can see, mains are closed, ties open. That's our normal configuration. And again, you've got control from this HMI screen. This is a picture of the control cabinet for the 600 volt switchgear. As the utility, our demarcation point into the buildings is a little bit different. We basically control the main time main for the low voltage switchgear lineup, and then the buildings group takes over past that. And that's true for both internal to U of A as well as external customers, at least in terms of operation. In terms of ownership, it's pretty much at the building wall, or the building, when it is built, has to pay for all the stuff inside the building, including the medium voltage switchgear that we operate. So the demarcation for ownership is different than the demarcation for operation. It's a little bit different as well. So anyway, this is just the cabinet for controlling that 600 volt switchgear lineup. Again, we're just concerned about the main time main. So that's all the buttons and lights are just associated with the main time main of that switchgear lineup. And then just a picture of the PLC inside and wiring associated with it. I don't think I mentioned yet, everything on campus that we have here is solidly grounded. So we have lots of ground bars, grounding, et cetera, all throughout campus, including the corridor system itself, interestingly enough. And that takes us around the hoop for that. So those were photos of the equipment that you're seeing here on this single line, as well as this single line is basically the same information again, plus the low voltage switchgear that we just saw on photos. How am I doing for time? I'm actually doing really good. So we have several different plants I talked about a little bit already. So this is the single line for our second cooling plant that was more recently built in 2010, the cooling plant on campus. So again, we've got a main time main arrangement. This is a direct supply from the south switching station. So there's two breakers, one on bus 1, one on bus 3, that feed down into this 15 kV lineup, which is in the cooling plant on campus building. Again, tie open, mains closed. We don't do automatic transfer at the medium voltage level. Everything at the medium voltage level is manual transfer, either remotely or locally, but ultimately manual transfer. From that 15 kV switchgear lineup, we go down to some step-down transformers. Again, dry type, cast coil. We standardized on cast coil, not so much because we have very harsh environments, but oftentimes our transformer infrastructure is in the basement of buildings, and it's one good way in case there is some kind of sprinkler system or flooding in that basement. These things, being cast coil, are quite rugged in terms of the environment they can be put into. So we've decided that we'll pay the additional percentage fee. I think it's around 15% to get cast coil for that ruggedness and that longevity. So anyway, step down transformers, then goes to 4160 volt here to feed some of the larger motors. So we've got 1400 horsepower, 300 horsepower. These are associated with our chillers that are associated with our chilled water system, which is of course used for cooling on the campus itself. So you don't see that main time main arrangement here. Instead, we've basically got multiple chillers. I think there is 5 in the cooling plant on campus right now. It's expandable to 8 on the floor plan. So you don't need all the chillers all the time. Even at the peak, we could run, I think, without 1 or 2 of those chillers in service. So we didn't feel like we needed that level of redundancy in terms of a main time main configuration. So we've done operational redundancy as opposed to electrical architecture redundancy. We did do a main time main on these because these are primary pumps that are VFD driven for the chilled water plant. Same thing over here in terms of those chiller supplies through medium voltage motor control centers. Over here, just like in the buildings, we've post-coupled these step-down transformers to the 600-volt switchgear lineup. Again, in a main-time-main configuration, again with an automatic transfer system that's PLC-based with an HMI that has controls again back to our DCS system. Our DCS system is in multiple locations. It's the heating. We have a control room in the heating plant, both cooling plants. So we can control, and the electrical shop. So we typically will control from the electrical shop or remotely or directly on the site itself through the HMI or push buttons. But we could, in an emergency or if needed, we could operate the electric system from any of those control rooms with the proper passwords put in. So that is the cooling plant on campus in terms of its single line architecture. The heating plant is quite different in terms of its architecture. We've got, again, 3 breakers from the south switching station, 1 from each of the 3 buses. So again, we've got truly at least 2 supplies here, all the way up to the EBCOR Garneau substation level, giving us lots of flexibility in terms of power flow. We've got 3 diesel generators that are used for black start. These are 1.5 megawatts each, and they live on bus 2. So we've got a 3-bus system. Today we operate with the ties closed and only one source that's active, with the other feeder breakers, the other main breakers, I should say, open. The only reason we're doing that is the diesel generator control setup was designed for a supply with an alternate. It wasn't designed for this third, so we're basically waiting for funding to replace the controls associated with this, at which time we'll go to a ties open system for the heating plant as well. But these do provide black start capability. The black start's very critical for us because if the heating plant ever loses power, we'd need these to black start the heating plant, which then in turn would help us to get one of our steam turbine generators going, if not both, which would then power the campus itself. They don't have enough capacity on their own to be self-sufficient as a campus. Again, they're about 15 MVA, 31 MVA, so that only adds up to around 50, which is our average load, I'd say. So during the peak of summer, when we're running all these electrically driven chillers, we're not able to be self-sufficient at this time. We're talking about adding another generator down the road, but that's going to be down the road. Anyway, getting back to the heating plant. So again, 3 buses only operating right now on 1 supply. This is step down. These are the transformers that we saw outside that step down from 13.8 kV to 4160 volts. So everything in the heating plant is 4160, which is why you don't see another transformer here for the larger motors, 4160 volt motor control centers. You do have step down to 12208 for plugs and lights and smaller things. Actually, this is 600 volt. My apologies. This goes to some VFDs that then run our air-cooled condenser associated with steam turbine generator number 2. Anyway, something that's kind of interesting about the heating plant in terms of its architecture, because it was built up in so many different phases, you get to see some interesting joint, I'll call it, or option supply points like this. And actually, we've got a project that's been going on for a few years now and will be going on for a few more years, where we're working towards upgrading, replacing a lot of the low voltage infrastructure electrically that's in the heating plant right now. Moving past that, talk a little bit about the original cooling plant. Was built in the 60s and 70s. So the architecture is very similar again. This one's 3 breakers, 1 from each of the 3 buses at the north switching station, again with main configuration. Again, with remote protection and control cabinet, with remote electrically operating capability from both an HMI touchscreen as well as our DCS system. One thing that is kind of interesting, we've got our largest chillers at this original cooling plant, so 2650 horsepower. I've certainly heard of larger motors, but those are the largest ones that we have, but they're directly operated off of breakers in the north switching station. So the 13.8 kV breakers are used to operate these 4 chillers. how the system was originally configured. We get down, so this is 13.8 kV switchgear again, a whole bunch of transformers to go down to either 4160 or again 600 volt with main time main, again with automatic transfer systems associated with the cooling plant. I'm actually running out of stuff to talk about. That went faster than I thought it would.
Well, how about if we give you a minute to think about and take one or two questions. Jim, you had one? He might have to unmute himself. Kane, anything?
I don't have anything right now. It's interesting that you guys have been using the Delta V distributed control system. I used to work for Fisher Rosemont a couple of years ago, and that's excellent system. You guys are doing good stuff.
The cooling thermal storage basin, I'm just curious how many gallons is that?
Oh, there's a great question. I have that off the top of my head.
I'm just curious. We got one at our place, and we've had some trouble getting it properly controlled. I think we got it under control now. It's a 1 million gallon tank.
Yeah, I'd have to look that one up. I think it's got about 5 tons. No, it must be more than that.
I think it's our cooling load is around 3,000 tons off this basin, and it's good for about 6 or 8 hours. So I'm not a mechanical, so I don't understand it as well as I should, I guess.
It's about 5,000 tons off the top of my head. I know it contributes overall, but it certainly wouldn't be enough on its own. I think it might be enough on its own at our minimum load, but certainly not at our maximum load.
The thought was that it would help run during the day to control the demand and then recharge at night with the demand charge being low.
Exactly.
But,
Okay, want to carry on, Lorne, or any other question? Is that here, Raymond? Do you have a question? Okay, go ahead. Go ahead, Lorne.
I've heard of other thermal energy storage systems, which I think are used for electricity storage, which uses But it's interesting that same name, very different. Maybe one other thing I haven't mentioned is on our protection and control, we do have an IEC 61850 communication network that's set up in certain areas right now. We've got a loop of loops fiber optic infrastructure in place where we have a backbone and we have some secondary rings in service. It's basically a long-term project, but certainly certain pieces of it are operating for zone interlocking. For instance, the south switching station has got full zone interlocking using IEC 61850, which then reaches down over to the cooling plant on campus for zone interlocking as well.
See, I think that there was a question that popped up on a power factor correction. How are you doing that with your medium voltage chillers?
We do have some capacitors that we have on just large motors. I believe the chillers, let me go back to that single line. Nope, close. Yeah, so you can see them here.
Oh, yeah.
We just chillers directly associated with the individual motors where it's required.
Okay, 10-4.
Any other questions? I know that was a lot of information in a short period.
Do you need more time to think about what you'd like to say, or I can unload some questions to maybe perhaps take the discussion in a different direction.
I think I'm basically done what I wanted to present. So yeah, any questions, I'll welcome them.
Well, okay, a couple of issues near and dear to my heart, apart from the technicals, and I'll get to the technicals in a moment, is how are you managed? You'd mentioned that you have a demarc between what would be considered the utility and then what a buildings group. You refer to a buildings group. How are you managed there? How is the electrical from the service at the utility to your district energy system down to the power outlet? How is that managed?
Well, again, there's two different demarcation points. One where the cost of ownership starts and one or stops, and one where operational the electrical utility. This is basically all us down to the building level. So in terms of once we get out of this sectionalizer, kind of the building wall is around here. Okay, so when this building was built, the building had to pay for all this equipment.
Yeah.
Right. From an ownership perspective, the building, and they'll call it the buildings group, owns this, and if it needed to get replaced, pay for it, just like they had to pay for it when it first got installed.
So they own the equipment. The department owns the substation.
Yes, but we operate it as the electrical utility. So for in terms of operation, we have our demarcation point right at this bus. So basically, they own, operate, maintain the feeder breakers down to the motor control centers and whatnot, and step-down transformers. We operate the main-time main and do maintenance on those.
Okay, so you mentioned feeder breakers. Do they also have control over the main breaker?
Oh, we have control over the main breaker.
Okay, so you can throw main breakers and primary switches, and then your guys are authorized. What about access to the substation room? How is that?
So we own the access to the substation room.
Okay, so you only have access. So the keying of the substation rooms, who owns those keys? The utilities group?
They're pretty much the only rooms in the buildings that we have ownership of those keys for.
Okay. And the department owns the square footage. Believe it or not, we've talked technical here, so I wanted to give another dimension to the presentation regarding how different universities manage the operation of their system. Jim can tell. Jim and I have some stories about how that's gone back and forth over the years. You want to add or subtract anything from what I said, Jim?
No, you hit the nail on the head. We got the problem in the U.S. that, National Electric Safety Code and National Electric Code has a division of sorts that's kind of not clear cut in many people's lives. Do we have that same kind of condition in Canada? Or do you appreciate what I'm asking?
No, I appreciate what you're asking, and very much so, depending on, what utility you're talking about. In Alberta, we've got 4 or 5 major utility players, and just electrically. So, depending which utility you're talking about, depending on the type of facility, whether it's industrial or commercial, that demarcation point can certainly move. I mean, I've heard of the user. I've heard of it being owned by the utility, and it kind of flies back and forth depending on the specifics of that negotiated agreement.
Yeah, what about telecommunication rooms? Very often, telecommunication rooms, fire alarm panels, access to them. I guess this is a larger access issue, which is related to a safety issue. Are you sharing? So you're a relatively new campus, so ours go back a couple hundred years, and I imagine that you don't have some of these legacy issues that we do.
Ours is about 100 years old, so we certainly do have our share of legacy issues. Not 200 years, but it started around 1913 in terms of a district energy system, and the first building was a little bit before that.
Mm-hmm. Well, I raise this because it's at least worth putting on more solid footing. This committee is largely technically oriented, and we're always under pressure to produce papers that are technical in nature. But there's this very large unexplored or uncharted or uncovered area as to how campus power systems are actually managed. And we have utilities. Everyone knows how public utilities are managed. Everyone knows how to manage a building, a building, an enclosure. Let's put it this way. According to the National Electrical Code, what a building premise is at the building service. This vast 110 to 200, maybe 300 megawatt building premises wiring system and its management very often are larger than, are much larger than individual public utilities. So I ask these questions because I would like to branch out into some of these areas, keeping in mind that we all have technical problems, but I believe that to help career support, very often it helps to vet some of these issues. My hope is in the future that I can have another conference, or at least another teleconference, among different organizations that are dealing with some of the jurisdictional issues between building managers and what are the utilities group. It's fair to say, Jim, maybe you want to characterize the cultural difference between the utility group at U of M, much of which I created, and the building electrical people. Do you want to hazard some opinion on that, Jim? It's a recorded line.
I started off by talking about politics. The hospital at one time had its own maintenance group, and as time passed, it was contracted over to the plant. But the hospital still maintained its own high voltage equipment, and things have transitioned in the last 5 years, Mike, maybe 10, where the hospitals can no longer handle their own high voltage switching, which is more of a must do now, and have to turn it over to the campus utilities group, which doesn't sense the urgency sometimes that we feel we need at the hospital. So there's been a little conflict there. But we've been working on it, and things have been improving dramatically as of late. But it was a little rough road for a while.
Didn't have to be.
Does that cover it, Mike?
Yeah, that's fair. It didn't have to be rough. You have a hospital there.
As an aside, I've been here for 30 years, and the hospital, although we both work for the same group of regents, the hospital and the rest of the teaching campus sometimes act like they don't work for the same boss. Anyway, enough said, since there's a recorded line.
Yeah, right. You have a hospital there, do you not? You have a very good
we got a
hospital. How do you, is that a culture unto itself? Do they have their own work group, their own priorities, their own rules? How's that managed?
I mean, it's totally different. It's a different branch of the government, and then all the way down they have people that manage the building. They have their own electrical trades group that does the work that's required to maintain the hospital, inside the hospital itself. But, I think we got kind of the best of both worlds in some ways, because, we've had a long-term understanding that we operate as electrical utilities the medium voltage equipment inside the hospital on, even though the hospital has ownership of it, we operate it on their behalf, or we operate it for them as electrical utility. In recent years, they've started to do their own, bring in their own contracts for maintenance. We used to do maintenance there, but we've had some challenges in terms of not only our own resourcing and availability of resourcing, but also we can't compete with private industry. We can't bid against outside contractors as a publicly funded entity. So either they have to choose to sole source us, or they have to go get contractors. So that's been an interesting kind of managerial hurdle in the last few years.
Yeah. Okay, let's see. We are coming on to an hour here. We've some of the technical issues I had were you're all solidly grounded. You mentioned that. Are you using what kind of cable? You mentioned cable. I spent a large chunks of my career dealing with the wiring and with the power density. What do you think is what is your average watts per square foot in a classroom? I don't want there's no average building, of course, but for the bulk of your square footage, what do you think? Let's say percentage loading of your service substations are.
Some of that in the last few years, and certainly, yeah, we're anywhere between about 30% to 70%. There's about 6 of our 100 buildings are above 80%, but the vast majority are, hovering right around 10 or less. And every once in a while that's good in terms of we definitely, that's even taking into account the requirement for the alternate supply through the transformer. Of course, you can't load that past 50%, right? But even with that into account, they're still quite lightly loaded in general. In terms of cabling, I know aluminum's near and dear to your heart, but with the space that we have in the corridor, you can see this, with the kind of the cabling infrastructure in the corridor was a bit of an afterthought. So we've stuck with standardized with copper base constraints and whatnot. So we standardize on 500 MCM and 2-watt sizes, so we have some spare reels in our yard in case we ever have an issue, which we have had a few times in the past.
Mm-hmm. Well, I try to point out that even if you aren't using building wiring, aluminum building wiring, which Jim and I put in the hospital, how much did the Children's Hospital cost us, Jim? Almost $1 billion, huh?
$750 million.
$750 million, and we built the football stadium with another quarter more than that. We probably put up about $2 billion worth of billion dollars worth of buildings in aluminum, and just this cycle.
Can I clarify that?
Go ahead.
At the hospitals, our main 13A district, our main feeders out of the substation were aluminum, but branch circuits were not aluminum. Just a clarification, right, Mike?
Yeah. One of the arguments I make, and I bring Paul Kemp tonight here to defend himself in Notre Dame, but you can build backup feeders for reliability purposes. If you need swing buses and you want to be able to build them some redundancy, some ability to reconnect in other places, getting a mile-long feeder built to be able to have that capability, even if you're limited by a 4-inch PVC, is still a great deal. Is a great advantage, and it can pay for itself. Very often these power outages, sometimes they're $1 million a minute in some areas. So I only mentioned that, and we did make progress. We finally got those 2 words in the U.S. National Electrical Code. Finally, and there's no finally, there's plenty to talk about. But the one of the issues that I think we're all struggling with is this idea that there could be more, because of the Ohio State power system getting sold or on the process of getting sold. I think we're all aware of what dangers might be there. Obviously upper management is very interested in the money, but of course we would still be charged with with running the thing. But I'm getting ahead of myself here. I wanted to close with that issue, but I first wanted Lorne to spend a couple minutes just buttoning things up here before we close out the call. Go ahead, Lorne.
So the weather thing, maybe I just thought was kind of interesting. We actually have an LRT system that we are the alternate supply for the LRT. So they get their normal supply from EPCOR through this main tie main arrangement. So usually this main's closed, this tie's closed, our main is open. But when they have to do maintenance on this or their supply or whatever, they do switch to us. And this is actually a traction substation, so the train power is actually coming from us, which is maybe a little unique as well. So again, any kind of a campus distribution system, certainly can have branches out to other places. We typically do feed hospitals and government institutions, but it certainly can be more than that, which is just kind of an interesting aspect of things. And I think that's pretty much all that I had to. Yeah.
Okay. Well, I'll take the screen over. Kane, any questions?
No, I don't. This is an excellent presentation. I really enjoyed it. Very, very good.
Yes, it was. Yes, it was.
Very well done, Kane. Lauren, you do have another person, Murray Sloan. Murray, are you, sorry, it looks like you came on later. Did you want to introduce yourself? Thanks, Lauren. Oh, so there's Raymond Moe. It looks like a couple of guys. Well, I'm not sure where Murray Sloan came in. But Murray, if you want to send me an email and identify yourself, it'd be nice to know who you are. It'd be nice to reach out, put you on our mailing list. So let me cut back over to our main page then.
While you're cutting over, can I just remind everybody that the Industrial Commercial Power Systems Conference for 2017 is going to be in Niagara Falls, Canada, coming up the second week in May. Might want to look into that and come over and visit Niagara Falls.
That is in Canada. We were thinking of you. Lauren. But next time we'll have to have one over in another your neck of the woods. We actually did, though. I have to say that Lorne was very collegial, getting us to the University of Calgary, right?
Yeah, that's right.
Yeah, and Ann was very, very collegial. I appreciated that very much.
We had 3 conferences in Calgary, but we had one of INCPS in Edmonton also, I believe, didn't we, Lauren, about 10 or 15 years ago?
Something like that, yeah.
I thought so. I said that to a couple other people, and they thought I was crazy. So there's at least you and me that think the same way.
Well, we have, who's it, Rashik that's out there?
Rashik's out down in Calgary. You're in Edmonton, right?
That's right.
Lauren?
Yeah.
I thought we were up there.
There's a lot of very skilled engineers up there, obviously, because of the oil industry. And
Right.
those guys are into some serious stuff up there. So, okay, colleagues, I very much appreciate your time. This might take a little while because I'm going to run it through our video guy, Mike Toner. I hope you don't mind. It might take as much as, I hope not much more than a week or two. In the intervening time, I'll be here. And I think we also know when the meeting is going to be. I think it's May 9th. When is it? I'll be trying as best I can. Right.
May 7th through 11th.
Mm-hmm.
Right, and we actually,
Or 8th through 11th.
Yeah, boy, I thought I had the time here. Anyway, I'll try to make it possible. Sometimes these organizing committees are not fond of patching in. That's a cultural problem we have to deal with, but in time it'll go away. We just have to wait it out. Just like with disc relays, right, Jim?
Yes.
Remember how Ram Sari said, I'll be damned if I'm ever going to put a electronic relay in. And I remember him pounding his fist. There's nothing like a Westinghouse CO9 or even
all you need is
Westinghouse.
all you need is a tap and a lever position.
Right. Anyway, those are the good old days when we look back. So, hey guys, thanks a lot. I'll see you on the Worldwide Inner Tubes. Yeah.
Thank you. Bye bye.
Yeah. Bye-bye.
Okay, sounds good. Thanks a lot.
Yeah. Bye.